4.7 is L'Hopital's rule. And L'Hopital's rule is a way that we can evaluate limits. Now, to use L'Hopital's rule, first it needs to look like a fraction. So before you can start using L'Hopital's rule, you need a numerator and a denominator. And sometimes you got to use some math tricks to make it look like that. But how do you know when you can use L'Hopital's rule? You can only use L'Hopital's rule when you evaluate the limit and get an indeterminate form. And an indeterminate form is just a form of an answer that we can't determine what it is. So the trick is we write the function as a fraction, and then we take the derivative of the top, and we take the derivative of the bottom, and we try to evaluate it again. And if we still get an indeterminate form, we take the derivative of the top, we take the derivative of the bottom, and we evaluate again. The trick to L'Hopital's rule is you never need to use the quotient rule. You don't have to think about it as dividing those things. The way L'Hopital's rule works is you just take the derivative of the top and take the derivative of the bottom separately. So let me show you what indeterminate forms look like. If I go and plug in the value for x, and the value I get out, the y value, could be one of these. These are the most common indeterminate forms. Infinity over infinity. Is that 1? Is that infinity? Is that 0? We can't decide. So we indeterminate. It's an indeterminate form. 0 over 0. Is that 0? Is that undefined? Is that 1? Infinity minus infinity. 0 times infinity. 1 to the infinite power. 0 to the 0 power. Infinity to the 0 power. Those are examples of indeterminate forms. And the first 4 on top are the ones that are the most straightforward to deal with. The forms on the bottom usually require you to use a natural log to get the x's out of the power. So let's look at an example here. This is the limit as x goes to 0 of sine of x over x. This is a limit that you could memorize, and in chapter 2 I think they anticipated you memorizing it. But it's kind of a waste of time in a sense, because in this case when I plug in 0 for x, I get sine of 0 over 0, when the sine of 0 is just 0. So I get an indeterminate form, which is 0 over 0. So what that means is I can use L'Hopital's rule. L'Hopital's rule says take the derivative of the top. The derivative of sine is cosine. And it says take the derivative of the bottom. The derivative of x is 1. Notice I didn't use the quotient rule or anything. I just took the derivative of each. Now I try to evaluate again by plugging in 0 for x. And this time when I do it, it works. I get 1. So what that means is the original limit is equal to that as well. L'Hopital's rule says if you take the derivative like that, the limit doesn't change. So let's look at another one of these. Notice it was a fraction when we did it. Here's another. X squared minus 2x divided by 8 minus 6x minus x squared. Let me change this a little bit. I think I got this problem written in here incorrectly. I do. So here's the problem written in its correct form. X squared minus 2x on top, 8 minus 6x plus x squared on the bottom. And I take 2 and I plug it in for x. 2 squared minus 2 times 2 is 0. 8 minus 12 plus 4 is 0. I get 0 over 0 again, which is an indeterminate form. So I can use L'Hopital's rule. And what it says with L'Hopital's rule is I can just take the derivative of the top, which is 2x minus 2, and the derivative of the bottom, which is negative 6 plus 2x, and try to evaluate now. If I plug 2 in now, on the top I have 2, and on the bottom I have negative 2, which gives me a negative 1. But L'Hopital's rule says the original limit is equal to that as well, because you don't change the limit when you take the derivatives like this. This one here is another limit that we have to work through. This is the tangent of 4z divided by the tangent of 7z. So if we want to work through L'Hopital's rule, we have to make sure it's an indeterminate form. The tangent is the sine over the cosine. So when I plug 0 in there, I get the tangent of 0 on top and the tangent of 0 on the bottom. And the tangent of 0 is 0. So I get 0 over 0, which is an indeterminate form. So I can use L'Hopital's rule. And to use L'Hopital's rule, I have to take the derivative of the top and the derivative of the bottom. to take the derivative of the top, I need to use the chain rule. So the derivative of tangent is secant squared of 4z. The derivative of 4z gives me a 4. The derivative of tangent of 7z is secant squared 7z. The derivative of 7z gives me a 7. And now I can try to plug in. I have 4 secant squared of 4 times 0 is 0. I have 7 secant squared of 7 times 0 is 0. And you can see that those might cancel as long as it's not 0. But the secant squared of 0 is 1 over the cosine squared of 0, which is just 1. So the secant squared of 0 is the number 1. And so when I'm all done, I end up with 4 over 7. But L'Hopital's rule says the limit doesn't change when you take the derivatives. So the limit of the original function must have been 4 over 7. Let's look at some other ones. Here is a use of L'Hopital's rule that isn't the same as the last one. And this use of L'Hopital's rule, when I put 0 in for x, I get 0 times. The cosecant is 1 over the sine of x. When I put 0 in there, this goes to infinity. So as is 0 times infinity in here, I can use L'Hopital's rule. But the problem with L'Hopital's rule is it has to be written as a fraction. So this is the math trick we play to write it as a fraction. Well, in this case, the cosecant is already 1 over the sine. So this really is a fraction in disguise. This is x over the sine of x. Now, if I rewrite it this way and I plug in 0, notice I still get 0 over 0, which is still L'Hopital's rule. So I can take the derivative of the top and take the derivative of the bottom. I get 1 over the cosine of x, and when I plug in 0, I'm left with 1. So the original limit must have been 1. But wait, there's more. Make sure I have some room. Here's another limit. Notice when I plug in infinity, I get infinity minus infinity, which is an indeterminate form. So I can use L'Hopital's rule again. But before I can use L'Hopital's rule, I have to write this as a fraction. And as it sits, it's not a fraction. So to do this, I'd like to factor an x out and then play a little trick to get the x on the bottom. But I can't factor an x out yet. I have to rewrite that. So I'm just going to use some algebra. This is x minus. I'm going to factor an x squared out from in there because the square root of x squared will let me bring an x out. But if I factor out an x squared, that's like dividing by x squared. So I get a 1 plus 1 over x squared. And now we have to double check that that works if I put it back in. So I have x squared times 1, which is x squared. X squared times 1 over x squared is 1. Legal move. But now I can take the x squared and factor it out of the square root. The square root of x squared is just x. But notice inside the square root it's been simplified. Now I can factor an x out of this because I need to write it as a fraction before I can use L'Hopital's rule. Now here's the math trick. If ever you have two things multiplied together, but you need to write it as a fraction, I can write that x on the bottom as 1 over x on the bottom. Notice dividing by 1 over x is like multiplying by x over 1, so I didn't change anything. Except now I can use L'Hopital's rule because I have it written as a fraction. The limit as x goes to infinity. On the top I'm going to rewrite this as 1 plus x to the negative 2 to the 1/2. And on the bottom I'm going to write it as x to the negative 1, just so it's easier to find the derivative. Now I can take the derivative using L'Hopital's rule, because it's a fraction. The derivative of 1 is 0. To find the derivative of that piece, I'll need the chain rule. Negative 1/2, 1 plus x to the negative 2 to the negative 1/2. The derivative inside is negative 2x to the negative 3. On the bottom, negative x to the negative 2. Now before I go and plug in, I want to simplify this to see how it looks. Notice on top, I can cancel these 2's, and I can cancel the negatives. And so what I have here is, there's a 1 on top. On the bottom I have x to the negative 3rd, so it's an x cubed on the bottom. And a negative 1/2 means the square root is on the bottom. Negative x to the negative 2 is negative 1 over x squared. Oops, there's a limit in here, Brad. This is the limit as x goes to infinity. 1 over x cubed times the square root of 1 plus x to the negative 2 divided by negative 1 over x squared. So I'm going to simplify this, and then I'll try L'Hopital's rule again if I can't evaluate it. 1 over x cubed square root of 1 plus x to the negative 2 times negative x squared over 1. Notice the x squared here cancels 2 of those there. And this becomes the limit as x goes to infinity of negative 1 over the square root of 1 plus x to the negative 2 is 1 over x squared. And there's an x down there as well. As x goes to infinity, 1 over x squared goes to 0. And this thing is negative 1 over x as x goes to infinity. And 1 over x goes to 0 as x goes to infinity. So after all these simplifications and derivatives, I get 0 for the limit. So that must have been the original limit. Infinity minus infinity does equal 0 in this case. But notice I had to rewrite it a funny way to get this x factored out and then to write it as a fraction. But once I did that, L'Hopital's rule worked. So here's the last one I want to do. These ones are tougher because these are the ones that are to powers. So if I want to find this limit, I have x's in the base and in the power. So to take care of that, I have to introduce a natural log so I can bring that down. So what I'm going to do is I'm going to name my limit y. So later on when I work with it, I'll be able to realize what the original limit was. And if I want to get that power down, I'm going to have to take the natural log of both sides. You say, well, why did you do that? Well, on the left side it didn't do much. But on the right side, because of the natural log properties, I can take the 2x and write it in front of the natural log. Now again, I'd like to use L'Hopital's rule to find this limit, but it's not a fraction. But we can play that limit game, or the fraction game. I can write 2x as, or I can write the x there as 1 over x in the denominator. Dividing by 1 over x is like multiplying by x over 1. As soon as it gets like this, I can take the derivative. Notice I'm not taking the derivative of this side because y represents my limit, and my limit doesn't change when I use L'Hopital's rule. On the right side, I'm going to take the derivative. The derivative of 2 ln of x is 2 over x. And remember, you can think of 1 over x as x to the negative 1. So the derivative is negative x to the negative 2. And I'm going to simplify this a little bit. This is 2 over x divided by negative 1 over x squared, which is the limit as x goes to 0 of 2 over x times negative x squared over 1. Notice the x squared on top cancels one of the x's on the bottom. And this becomes the limit as x goes to 0 of negative 2x, which is 0. So what I've just found is the natural log of y equals 0. But notice, I want to figure out what y is, because y is equal to the limit that I'm looking for. So to figure out y, I have to undo the natural log I put in there. And the way you undo the natural log is you raise everything to the power of e. So I got that y, which is the limit that I was looking for, is equal to 1. So I found that original limit, but notice I had to take the natural logs to make that work out.